Mm, Ano,
Hello, good evening.
Good afternoon.
start with the question first. The this is part of this question. Energy, but this topic is not energy. So, the principle similar. This case is using cascade analysis. Energy and material energy and water saving from greenhouse gas emissions to emission major center and population. So, numerous studies have been performed on the subject of improving energy efficiency while reducing emission of greenhouse gases. The environmental harm as when we become evident that resource and everyone of gesture processes are very charging. This process integration the family of methodologies who combine from the processes to reduce consumption of resources in order to reduce harmful emission. This energy saving methodology have been used extensively in the processing power generation for the past 30 years. Heat integration examines the potential for building in order to reduce the amount of so the difference between what we see yesterday is reduction of cost, reduction of the cost, reducing fresh water consumption. But for energy wise, it's to reduce the external heating, meaning no need to install or but to harvest the heat from the existing process via from the the role of PI, process integration, in making industry sustainable. Sustainable development implies that current action should not harm future generations and that measurable indicators are needed to ensure compliance. For industrial processes, the relevant indicators are the rates of resource intake production. So this factor usually expressed in terms of footprints, for example, the carbon footprint. The one we have for methane footprint, water footprint of process. The sustainability of industrial process depend on minimizing this footprint. For synthesis and design problem, the major indicator should apply to the process system complete life cycle as part of a successful assessment. Example of applied process integration. The integration of hospital services real case study. The study hospital contractor include the general hospital within a 1% for example, under public building. The diesel fuel used to generate the steam required for the complex to 75% total energy consumption and 68% of its total energy cost. total energy cost. The pitch analysis that was performed estimated the minimum need for external heating and kilowatt because the actual heating use was means 125 kilowatt. There existed a potential energy saving of 50%. So when they do the pitch analysis, we know of the three methods to do this analysis. Limiting composite curve, cascade analysis, or sourcing or demand source. So all of this method is to get the determine minimum fit for external minimum for this case hospital. It only requires 388 kilowatt, but the existing process is using 625 kilowatt, meaning they can reduce it. Wait. So meaning they can reduce it up to 38%. So heat recovery problem identification. The heat recovery problem data are extracted in several steps. This method is for heat. Inspect the general process flow sheet, which may include recovery exchanger. So when it's talking about heat recovery, there must be some method to recover the heat. So normally it's through heat exchanger. So heat exchanger for those familiar. So we have two strips, the counter current of both. So this two stream is hot stream. So this two meet within the exchanger will not mix together. Some of the exchanger is some mixing, but normally there's no mixing. So when they meet, they will transfer heat. So that one is the heat exchanger. All of them. Second one is to remove the recovery engine and test them with not sure if the Fabric cover this part. Alarm all consecutive heaters and coolers. The resulting virtual heaters and coolers represent the net heating and cooling demand of the flow sheet stream. The heating and cooling demand of the flowsheet stream are then listed in a tabular format. Each heating demand is referred to as a cold stream, and conversely, each cooling demand is example. This example is using cascade, a process flowsheet involving two reactors and distillation program. Why I choose this? Because at the end, later on, we will have a grand composite curve. Later, I will also show grand composite curve for what is now. It's process flow sheet with two reactors, one, two, and a distillation column. The process already incorporated to recovery changes. So heating demand process is 1,1760 watt and the liquid cooling demand is 920 kilo. Figure 4.4, this figure shows the flow sheet after step 1 to 4. So the first step, this is for heat. So you have a device process flow diagram. The heating and cooling demand of the stream have been performed with the have been left out of the analysis for simplicity, although this will be retained. It is assumed that any process within the T is available in heating. As you can see here, there is no more this assembly. So in figure 4.3, there's a heater here. This is simplified. Thanks step 5 of the data in figure 4.4 produce the data set preparation. So for stream H1, I have 4 stream. For the first stream, hot stream is from supply is 122. The target is 78. So there's a difference here. We so in water we use source C, but for heat it's supply and target. Similar. So in this case, supply means inlet. So in, uh, water is sink, and for target is source. For this case, hot is from 143 to 78. Delta H is negative 2018. So CP need to be calculated. Well, normally delta H, you may need, if not given, you may need to calculate it using energy balance, but normally it's given. For H1 is for cooling here, 80 kilowatts, inlet 182, outlet to the column is 72. For stream H2, as well, for 124. Here, cooling. And for coal is 3 at corridor here, 52 in is to 100 degrees C. The last one is vector. So vector 1 I have 2 inlet, going to vector 2, then pulling straight through the. So CP can be calculated by delta H over TT minus TS. So TT here is the target, target, minus temperature supply, delta H over delta T. Delta H is normally given, or you can calculate it through CPDT, some regression. That one is infinity value. Problem table algorithm. It's similar to cascade analysis. The concept, although composite curve although composite curve can be used to set the G target to inconvenient since they are based on graphical construction. So that's mean the much accurate method is cascade analysis. Although you need to calculate one compared to the algorithm will be explained using the data in table 16.2, 16, or delta T mean equal to 10 degrees C. So delta T mean for liquid is normally similar, it's 10 degrees C. But for gases, meaning inside this stream, for this case, for this process, is liquid. If later on, if the process is involving some of the stream is using gases form, for the delta T mean is actually 20 degrees. What is rule thumb is the explanation how to choose it, but normally for liquid 10, for gases 20. Why we need delta T mean? Delta T mean later on we need to shift the temperature. And determine the shifted temperature interval, this is the method. From actual supply and target temperature, hot stream are shifted down in temperature by delta T mean over 2, so 5. Well, delta T mean is 10, 10 over 2 is 5. Cold stream up by delta T mean similar, 5 degrees C. Is detailed in 16.3. So for temperature supply, for temperature supply is depend on the cold and hot type. For example, stream 1 here, cold stream. So for cold is up by 5 degrees. So plus 5, so 25. Shifted TS is 25, shifted TT, temperature target is 185. For hot stream is down by 5 degrees C, plus 30 meter 2. So from 250 to 245, from 40 to 35, and so on for other stream. The stream population is shown in figure 16.16. With vertical temperature scale, the interval temperature shown in figure 16.16 are set to delta T mean to hot stream. This one you already done it in step 1, but the table 16.3. The next step is to draw this figure. So y-axis here is the shifted temperature so from 25 up to 245. And the temperature here next to the arrow is the actual temperature for stream 1, the temperature supply and temperature target. So plot for all the stream 1 is from 25 to 185. Stream 4 is from 195. to 75. Heat balance is carried out within each shifted temperature interval according to the equation below. So need to calculate the delta H for internal. So although given such a system or such equation, it's delta H, but after the shifted, need to calculate the heat balance for enthalpy for H here is enthalpy for temperature. So CPC minus CP cold minus CP H times delta T. So once you draw the this diagram, next is to within the same diagram, just extend it to include 1, 2, 3, 4 column. So each column have row that is between the temperature of the interval temperature or shifted temperature. So meaning for here 25 to 35, sorry, 35 to 75, you have a gap of different of 40 degrees C. The CPC, CPH is 0.005. How do you know? CP here given 0.2. CP is based on table 3. Table 16.2 with the CP, so vector 1 or stream 1. CP heat capacity is 0.2, stream 2 is 0.15. So going back to this table, so 0.2 minus 0.15 given here, CP 0.05, then we need to calculate new delta H, delta for internal. So 40 times 0.05 is 2. The result is given in figure 1670 with some restricted interval as given. We have a surplus of heat and some have a deficit. The heat balance within each restricted interval allows maximum heat recovery within each interval. However, recovery must also be allowed between intervals. Also, CP calculation, for example, 35 to 75. That's what I'm doing. So why CP1 and CP2 minus? Because the line for the arrow for second stream and first stream is within this gap. So for example, stream 2 at 45 to 235 is alone. See here. So the equation is CP whole minus CP hot. So 2 here is hot stream. So 0 minus 0.15 is negative 0.15. So the interval here is 10, you can see. So 10 times 0.15 is 1.9. So what is the surplus? So once this ready, you can plot the cascade. Similar to water cascade analysis yesterday, we start with 0, 0 from 0. Cascade any surplus heat down the temperature scale from interval to interval. This is possible because any excess heat Any excess heat available from the hot stream in an interval is hot enough to supply a deficit of cold stream in the next interval down. First, assume no heat is applied to the first interval from hot utility. Figure 16.18a, this figure, the first interval has a surplus of 1.5 megawatt. So how they get the 1.5 megawatt is 0 minus negative 1.5. So delta H here refer back to delta H internal, this column. Then so on 1.5 minus 6 is negative 4.5 until negative 0.225. Eh, 0.25? No, 2.5. This one is 2.5. Okay. Some of the heat flow in figure 16.18a are negative, which is invisible. So we cover yesterday. There's a negative. We need to choose it as the highest negative, the biggest number will be huge. So that number will be added to the static hot utility. To make the cascade visible, sufficient heat, sufficient heat. So how much is sufficient heat is based on the highest negative value, so 7.5. So 7.5 from hot utility, it must be added from the utility to make the heat flow to be 0. The smallest amount of heat needed from hot utility is the largest negative heat flow from figure 16.18a. That is 7.5 megawatt. In figure 16.18b, this figure 7.5 megawatt. So from hot utility to the first 7.5 minus of come plus 1.5. So 9. So on here you put 0, 145. Increases all of the heat flow between interval by 7.5, giving one heat flow of just 0 at an interval temperature of 145 degrees. More than 7.5 megawatt could be added from the hot utility to the first interval, but the objective, although so you can put like 8 here, 10 megawatt, but the objective for pinch, so the water or gas pinch, is to find the minimum hot for utility for this case. Hence only the minimum is added. So the minimum is 7.5. The point where the heat flow goes to 0 and T shifted equal to 145 degrees C correspond to the pinch. Example. Flow sheet for a low temperature distillation process is shown. Figure 16.90. Calculate the minimum hot utility requirement and the location of the pinch, assuming delta T mean equal to 5 degrees. So from here you have two distillation column. The temperature is 20, this one is negative 90, 19, 20, 20. The difference is very small. Negative 1. First extract step 1. First extract the stream data from the flow sheet. This is given in table 16.4 below. So how to know hot or cold stream? So for hot stream, the inlet temperature or supply temperature must be higher than the targeted temperature. This one is hot. Yeah, this one is hot, of course. Negative 40, smaller than this. Cold because it's lower than the target, so it's cold stream. Yeah, all cold stream. Fit to column 1. Column 1 condenser. So condenser. Column 2 condenser. So column 2 condenser negative 39 to negative 14. For the concept, column 1 the boiler, column 2 the boiler, column 2 bottom, column 2 over there. So column 1 the boiler 19 to 20. Yeah. CP calculator based on delta H of the over T3 minus TS. So delta H, as I said, is given for this case. Yeah, 1 to 1, 0 to 1. So for hot stream, the delta H is negative. For cold stream, the delta H is positive. We calculate for CP. For hot stream, the delta H is negative, and vice versa, the hot stream. Hot stream can be identified if the supply temperature is higher than the one. Step 2, calculate the shifted interval temperature. Stream temperature are shifted down by 2.5. Shifted up by 2.5. So hot stream minus 2.5. Cold stream plus 2.5. How do you know 2.5 is based on the delta T mean equal to 5. So 5 for hot is delta T mean over 2. 5 over 2 is 2.5. So you have another column for shifted temperature supply and shifted temperature target. So for hot is minus 20 minus 2.5. So 0 minus 2.5. How about cold? So cold is plus 2.5. Then carry out the heat balance within each shifted temperature interval. So from here, based on the shifted temperature, the lowest is negative 41, sorry, negative 42.5, the highest is 2.5. So once you draw this line, how to draw this line is based on the shifted temperature. Then you plot the stream. Stream 1, stream 2, stream 3, all is hot stream. The arrow is going down. 4, 5, 6 is cold stream. It's going up. Then calculate the temperature interval. Then CP minus CPC minus CPH. So in this case, for example, from negative 42.5 to negative 51.5, only stream 3 exists. So the CP is negative 0.0.8. Why negative 0.8? Because CPC minus CPH. CPC minus CP. Then calculate for the delta H, 1 times negative, then get negative 0.2. Step for the heat cascade with 0 hot unity. So start with 0, dot all the shifted temperature. This is the delta H for internal. Then from 0, starting with 0 hot utility, so 0 minus 1, negative 1.2, so on. This lead to negative heat flow, the largest of which is negative 1.84. So 1.84. Adding 1.84 hot utility gives QH mean equal to 1.84. QC mean equal to 1.0. Similar, 1.84 as well. Although the pinch is at negative 21.5. Hot stream pinch temperature is negative 19. Cold stream pinch temperature is negative. After maximizing heat traveling in the heat exchanger network, those heating polarities are not serviced by heat travel must be provided by external utilities. The most common hot utility is steam. High temperature heating utilities require furnace nuclear or a hot oil circuit. Well, utilities might be refrigeration, cooling water, air cooling, and furnace heating. So this slide is talking about, yeah, we already learned about how to recover the heat. But for stream heat operation that is not covered by the heat recovery, then you need to supply external, either hot or cold utility. Then composite code. Tools to understand the interface between the process utility system obtained by plotting the problem table cascade. The picture plotted here is shifted temperature. So hot stream are represented by delta Tmin over 2 for the case. For state, so from here, the point of zero heat flow in the grain composite curve of figure 64 is the heat recovery pinch. Here is the pinch. How to get this graph? This is based on delta H, plot delta H versus shifted temperature. Then you get this zigzag graph. So here is the pinch. Open jaw at the top, bottom, QH mean, QC mean. Here is the QH mean. This is the QC mean. The shaded area known as pocket represent area of additional process to process heat transfer. In the pocket in 16.24, a local surplus of heat in the process is used at temperature differences in excess of local daily satisfied local utility. This reflects the cascading of excess heat from high temperature interval to lower temperature interval. The problem table algorithm. Example, how to utilize when composite code. The problem table cascade for the process in figure 16.2 is given in figure 16.18 using the grain composite curve. For two level of stream, for two level of steam at saturation condition and temperature of 240 degrees and 180 degrees C, determine the load on the two stream level that maximize the use of power. The situation B, instead of using steam, the hot oil circuit is used with supply of 250 degrees C, and Cp equal to 2.1 to the control kilogram can be calculated by minimum rate of hot. So from this process, we need to do the temperature, to compile all the temperature first. Then need to calculate the shifted temperature. For this case, for this case, if we use the water heating equal to 10, so shifted is by 5 degrees C. Then calculate the delta H interval. You get the cascade. So from here, cascade, the minimum heat is 7.5 megawatt. It means 845 degrees. This is actually a similar question in before. Only difference is we're using grand composite based on this data given. So delta temperature shifted over delta H. Delta H is delta H interval. If you plotted it will be like this, zigzag. So the pinch when the curve touches the y-axis. At this moment is pinch 145 degrees. For delta T min equal to 10 degrees C, the two steam level are plotted on the grain composite curve at temperature of 245 degrees C and 175 degrees. Figure 16.2a shows the load to maximize the use for lower pressure steam. Calculate the load on the low pressure steam by integration of the cascade issue to support so for load at 180, we don't have the data, what we can do interpolation here based on pinch. Why you choose pinch? Because it's data has zero. So 175 minus 155 over 155 get 3 megawatt. A lot of 240 based on this temperature. Approximation and the temperature of 240 and 180. So you have calculated for 180 the load. You mean the load on the two steam level. But for 240 is 7.5 minus 3. Not 140 4.5 meter. How about this one is for steam? How about oil? Uh, for hot utility. Figure 16.26 shows the grand positive with hot oil providing the hot. See, this is a similar graph. Similar. If the minimum flow rate is 5, then this corresponds to the steepest slope and minimum temperature. So for this problem, the minimum temperature for the hot oil is each temperature. So each temperature equal to 155 is and T equal to 150 for hot steam gas. To calculate the minimum flow rate for hot oil, starting from 0, touching the line here, and stop at 280. Why 280? Because supply temperature hot oil is 280. From the 280, you can get delta H of 7.5 megawatt. 7.5 times 10 to the power of 3, which is mega. 1 over 21, 2.1 is Cp for oil. And this one is 1 over 280 minus 150. So you get 275, 275 like that. So we have learned how to plot the gen composite curve, which is from the T shifted to delta H here. What is the purpose of gen composite curve? We can find the load, this is for steam, and if we want to use instead of two is something else, we need to know the Cp and the supply temperature. From the supply temperature, you can calculate the minimum flow rate for this. Indication next is about method use. This topic is 5. Quite easy. It's about how to design the heat battery system from data from LCC. And those switches uh, taking info nuclear water. Okay. Next. So, what the system design? Oh, based on chemical, a book by Robin Smith, Chemical Process Integration. Slide. Previous slide we can avoid can teach with from it. The system design, chemical process design and integration of this meet is chapter 26. page 593, I given you the books. So, water use. Water use is for a wide variety of purpose, process operation, action medium, or liquid form, extraction process, steam stripping, steam ejector for production of vacuum, equipment washing, housing operation, and so on. One thing all of these operations have from the step. The water comes into contact with process material and become contaminated. Now, listen. Figure 26.11 shows the quantitative representation of this on the plot of concentration versus mass lot of contaminant. So here, uh, water in its concentration and inside the process is the transfer to get water concentration. It's like this one. So here, semin less load. So here, mass load of certain value. So once you input the water, it will slowly it will increase the temperature to the solution space. So if the flow rate of water to an operation is decreased by some changes to the pressure, then for the same mass load transfer, the reduction in the water flow rate will look to a steeper line and higher saturation in the sequence. The reduction in the water usage will be limited by either the operation requiring some minimum flow rate, below which it cannot operate, or the outlet concentration from the operation goes to a maximum value. If all operation use clean water, then using the flow rate to its minimum value can be used to minimize the water consumption as illustrated in this figure. However, such an approach misses the opportunity to reduce the. We see out here is the contaminant. So higher outlet concentration, more contaminant means less water. To open up the ability to reuse water between pressure. Some level of inlet contaminant must be accepted. Figure 26.13 shows a water using profile such that both the inlet concentration and outlet concentration have been set to their maximum values. Output is similar. However, Cin is not. This particular setting, where both the inlet and outlet concentration are set to the maximum value, can be used to define the emitting water profile. As shown in figure 26.14, the limiting water profile is used to define a boundary between feasible and infeasible concentration. The concentration of water profile is considered to be feasible as long as it's below the limiting water profile. So the line for limiting water profile. So anything below the limiting water profile is the feasible water stream. Getting maximum water use for single contaminant. To illustrate how the overall minimum water consumption can be targeted when allowing reuse, consider the data for the simple problem given in table 26.4. We have 4 operations. Contaminant mass is 1,000 for first stream. In that is 0 to 100 ppm. So limiting water flow rate here is ton. T is ton per hour. This one is gram per hour. And to calculate limiting water flow rate is only 2,000 over 3,000 divided by 100 or 5,000 divided by 50. So 2,000, no need to change the unit. So 2,000 gram per hour divided by 100 minus 0, so 100 ppm. We get the 20 ton. It's similar. So here is 4,000 divided by 400 is 10. The concentration is specified on the basis of the mass flow rate of water and not the mass flow rate of the mixture. So C is equal to MC over MW. It's not C over the mixture. So meaning MC over MW plus MC. So in which C is the concentration in ppm. So MC is the mass flow rate of contaminant. So C here is equal to contaminant. In gram per hour or gram per day. MW is mass water flow rate for water in ton per hour or ton per day. So this unit to make sure if it is not the same unit. The other point to note is regarding the unit. It is convenient to define the flow rate in terms of strict tons. Typically ton per hour or ton per day. It is also convenient to define the concentration in terms of part per million. If the basic unit of flow rate is taken to be tons and concentration to be part per million, then the mass loss is measured in gram, typically gram per hour day. This is just explanation about the units. The limiting water flow rate is the flow rate required if the specified mass of contaminant is picked up by the water between the maximum inlet and outlet concentration. So between the C in and the C out. If an operation has a maximum inlet contaminant concentration greater than zero and spread by water with zero concentration, then for the specified mass not or lower flow rate, then the limiting water flow rate would be analysis of the data in table 26.4 can be started by calculating the flow rate that would be required for each of these situations. Remember 26.4 you have 4 streams, each with different different C in C out, different value, the contaminants, right? The relationship between mass pickup of a mass flow of water and concentration change is given by delta MC equal to MW delta C. So this equation is actually delta C, sorry, C equal to MC over MW. Yes, this one, 26.1. C MC over MW. In this case, there's a delta. Delta means reference. So in this case, delta C mass pickup of contaminant to flow rate of water and concentration change. C in and C out. For fresh feed and minimum flow rate for the stream, from table 26.4, you can calculate the mass flow rate of water, the fresh water feed. So talking about fresh water feed, so all is starting from zero here. So 2120. Second stream is 50. So on the total flow rate of fresh water is 125. Consider now the possibility of reuse. Now you know this is the total flow rate. Fine. Meaning without reuse. To determine the maximum potential for reuse, figure 26.50 shows the four operation plotted on concentration versus mass load. Note the concentration maximum inlet on outlet concentration limiting. So this is limiting composite. And here is from 0 to 100. This is from 50 to 100. This is from 50 to 800. So on. So this first, so you have 4 arrow. No need to combine it. No. Later we will combine it to make a composite like this. Figure 26.15b shows limiting composite curve of the four water stream. To construct the limiting composite curve in figure 26.15b, the diagram is divided into concentration interval and the mass not within each concentration interval combined to obtain the limiting composite. So then you combine to get the limiting composite curve from here. One, okay. To target the minimum water flow rate, a water supply line is drawn to represent the water supply. Draw the water supply line. So the moment the water supply line touch the limiting composite curve here and 100 ppm, you can see that one is the pitch. In this case, the minimum flow rate is 90 tons per hour. How to get 90 ton is 9,000 over 100 ppm. If the minimum water flow rate is to be obtained, the steepest line possible must be from this line. This is shown in figure 2616, where the steepest slope corresponds with the water supply line particularly. Okay. So now you know how much the minimum flow rate we can power, how to know the each point. Next is to design for maximum water reuse for single water window. So having seen how to set a target for the data in figure 26.16, consider now how to achieve the target in design. Figure 26.17 illustrates the basis of the design strategy. So from here, you know how much the minimum flow rate is. 90. So you have two parts of the composite curve. First part is below the pitch. Second part is after the pitch. So from 90 goes here. From here, this is the pinch point. From the pinch point, only 45.7 ton per hour going after the pitch, while the rest goes straight to the water treatment. So how do you know 45.7? How do you calculate the 45.7 ton per hour? This one is based on the composite curve from 41 to 9 here. We already know below the pinch is 9,000 over 100, right? So you get 90 ton per hour. But for after the pitch is actually 41 minus 9. So 1 minus 9 times 1,000 is 32,000 divide by 700. So why 700? From starting from the pitch here is 100 and at 800. So 800 minus 100. So you get 45.71. That's how you know that only 45.7 goes to the next, and while the rest is goes straight to the water supply and water treatment. The design region are defined by a straight line drawn between the convex point. This is the straight line, the dotted line, to identify the pockets in the problem. The basis of the design. So for this case, we just see the pockets for heat before. So the pocket is for heat recovery. So this case is water. The basis of the design strategy is to use the target flow rate below the pinch, and then to use only the required amount above the pinch, with the balance going to effluent. So 44.3 clear straight to the effluent, 45.7 required after the pinch. Having formulated the basic design strategy, the grid can then be set up shown in figure 26.18. Okay, this is design grid for the water system. The design grid start by setting up 3 water mains. So you have 3 water mains here, means the column here. You have 3 columns. First column is freshwater feed. Until you see there's no contaminant, so 0. Next is pinch point. From here 45.7, while 44.3 west we goes back to the effluent. The 45.7 we go next level up to 800 ppm. Here there's no fresh water now at 800 ppm. All of it is converted to wastewater. Okay. The design grid start by studying up to the main corresponding with freshwater concentration, pinch concentration, and the maximum concentration. So the limiting flow rate here is refer back to the table. If it's not given, you need to calculate. How to calculate this? Minimum, how to calculate? Contaminant mass divided by concentration difference. Yes, this one. Then you get the water. So here is the first stream, 0 to 100 ppm. Refer back to the table. Here is 50 to 100. But for stream 3 here, it's actually from 50 to 800. So means it's going across the second water main, 100 ppm. But then it must back to 800 ppm. But for the fourth stream, it's direct. It's 400 to 800. The flow rate required by each water main is shown at the top of the main. Okay. And that's alternated by the main at the bottom. Stream representing the individual operation requirement are superimposed on the water main. This one, stream 1, 2, 3, 4. Operation 1 is limiting data corresponding with fresh water at the inlet and 100 ppm at the outlet. It is therefore shown between the freshwater main and the pinch concentration water the main. So table 26.4 data for a program with 4 operations. Operation number 1, 2, 3, 4. This one is okay. Focus on first operation. So the inlet is freshwater, so 0. Then immerse at 100 ppm at the outlet. Is the version between the freshwater main and the pinch concentration water main. This one. The operation are then connected to the appropriate water main as illustrated in figure 26.19. So for this figure, this one is okay. See 20. Why 20? Why similar to limiting water flow rate? Because it's actually connected between the mains. From the first one, feed, pinch, the outlet. How about the second one, second stream? It started at in the middle between the mains from 50 to 100. You need to calculate this case from 0 to 5. Then MC referred to continuous mass 0 to 5. What the second one here? 5,000. Right? So 0 to 5. The concentration is from 50 to 100. So from 50 to 100 is actually 100 ton per hour limiting water flow rate. So from 0 to 100 is actually 50. 0 to 100 here is actually 50. How about the third one? The one is 50. So the third one is 30,000 contaminant mass, 30,000. However, operation number 3 is actually passing through the middle bottom main, pinch main. So meaning the concentration is the concentration is from 50 to 100 first, then from 100 to 800. So from 50 to 100, we need to calculate. For this case, it's 0 to 2, because why 0 to 2? Because this is from 0 to 100 ppm. So from 0 to 100 ppm, the limiting water flow rate is 20. This is 20 ton per hour. Sorry, 2000 gram per hour. So in kilogram is 2 gram per hour. So 0 to 2 from 50 to 100. So from 50 to 100. So the limiting water flow rate is 40. But from 0 to 100, 0 to 100 is 20. So 20. How about after the pitchment? That one is 40. This one is easy because see here, because at 0 to 100 ppm, we think that the flow rate is 20 or 2. Sorry, 2,000 gram per hour or 2 kilogram per hour. So here we start with 2 until 30. So 30,000 gram or 30 kilogram per hour. The concentration is not from 0, it's from 100 because pinch main is 100 until 800 ppm. So we get 40 ton per hour. See here, 28 divided by 700. 28,000 divided by 700. So 40. How about the last stream? The last stream have contaminant mass of 4,000, so 40 to 4. And 4 here is 400 to 800. 400 to 800 is actually 10 ton per hour. But because this line is from 100 to 800, so we have 100 to 800 for 4,000 contaminant mass. It's actually 5.7 ton per hour. So if you see here, this row, sorry, this column, this row, yeah, 50, 20, 50, 50, is actually balanced with the fresh water flow. How about this one is same? This one is in balance with 45.7. However, there is a problem created by operation flow. In that below, the pitch it receives a flow rate of 20 tons per hour of fresh water, but at the pitch it receives a flow rate of 40 tons per hour of water at 100 ppm. So this change in flow rate in the middle of operation flow would be impractical for most operations. So figure 26.19 also show the concentration and limiting concentration versus mass load the gradual operation. This in principle is a working design, but it could be practical if operation 3 involve, for example, an operation with multiple stage of washing. If this was the case, then the different stages could be fed with different flow rate and quality of water. However, for most situations, this change in flow rate would be completely impractical. It should be changes in flow rate within the operations. The change in flow rate for operation 3 is in fact readily corrected. Consider figure 26.20 theoretically, this one. We show the concentration versus mass load for an operation with a change in flow rate within the operation, similar to operation 3. So you see here, it suddenly changed the flow rate. This is a part 1, part 2. Where does it change between the part 1 and part 2? So unfortunately, I'm going to change the flow rate. So if the inlet is shifted before the part 1, so the arrow is actually in line with the second part. It's actually similar. It's actually sama. Yeah. If you do it like this, at the end, it will be shifted like this. If you transited the pin for the part 1, eventually it have a similar slope. Max balance around part 1 in figure 26. Give MWR and MW1 mass flow rate of water in part 1 and Cph minus E naught equal to MW2 Cph minus E next. Moving the mixing junction to the inlet of the operation as shown in figure 26.20 and carrying out mass balance in the new mixing junction give this equation. In which substituting equation 26.3, this equation, into equation 26.4, this equation will give a C in equal to C in maximum. In other words, if the mixing junction is moved from the middle of the equation to the beginning of the equation, then there is a constant flow rate throughout the equation corresponding with an inlet concentration for the mixing of the maximum concentration. Also, by definition, the flow rate will be the limiting water flow rate. So in figure 26.21, so we already know we can move the stream here. If we move the stream, at the end it will be the same. So in figure 26.21, change in flow rate for opening tree that previously occurred at the pinch concentration, what the man is now added at the concentration to the inlet of operation tree. So let's mean here we have a water release from the second main for 20 ton per hour. So it is actually from 0 to 30 instead of 2 to 30. So 0 to 30 from 50 plus 3 start from 50 to 1, sorry, to 800 ppm. The flow rate is similar, change in the design. Is 40 ton per hour, similar from for here and here. The design now features a constant flow rate in all of the operation and achieve the target minimum flow rate of 90 ton per hour. The arrangement shown in figure 26.21 involves reuse of water from operation 1 and 2 into operation 3 and 4 via a water main with consumption of 100 ppm. So an alternative way to arrange the design is to make the connection directly rather than through an intermediate water main. If the intermediate water main is removed, then there are basically two sources of water from operation 1 and 2 at 100 ppm and two sink for water for operation 3 and 4 at 100 ppm as illustrated in 26.52. So cross is 100 ppm here to operation 1 goes to operation 3, operation 2 goes to operation 4 with 44.3 goes straight to the structure. Figure 26.3, this figure shows this assessment in a grid diagram. And figure 26.4 shows the final design as a conventional flow sheet. So from here, 1 supply to 3, see, 20, then 50 goes to, sorry, stream 2, operation 2 goes to operation 4. In terms of flow sheet, it's like this. So we have a 90 ton per hour of fresh water. Goes to operation 1 is only 20, so 20. Goes to option 2 is 50. How do we know? We already calculated it. And from here, operation 1, another 20 is going to the operation 3. Operation 1 goes to the operation 3. So you have 20 is 40. For operation 2 here is supply 5.7. Operation 4 and wastewater generated is 44.3. The end wastewater is 50 ton, similar to fresh water feed. Consider figure 26.5 involving 3 water main, 3 operations. A number of issues to be considered and would apply to more complex problem. So here, the final condition of a stream might be below that of a water main. The water should not be discharged to water main until it has reached main concentration. So in this case, because it's not the second operation here, the C out after temperature, sorry, but situation is not up to this water main. So to redirect it to uh, operation 3. So meaning mix here until the concentration reach the last button. Operation 2 above the plane terminate at a concentration less than the concentration for the high concentration water. The outlet of operation 2 must not be fed directly into this final water. The basis of the mass balance from figure 26.17 dictate that all streams must achieve the concentration of the water main into which they are being fed, otherwise the mass balance will be violated. Thus, in this figure 26.25a, the outlet of operation 2 must not be fed to final water main but must be used again and brought to the concentration of the water main into which it is fed at figure 26.25b. Must be reused by the figure 26.26 shows a more complex limiting composite curve that involves three design regions. So you have three pockets with three design regions, rather than two. Before this, we only have two. The design region and 5 by straight line drawn between the convex point define the pockets in the problem. In figure 26, there would be 4 watermen. Instead of 3 watermen, they have 4 watermen right in the design grid. However, the basic principle are exactly the same as those described so far, but with the additional watermen or additional color. It is often the case that there is more than one source of fresh water available. There may be raw water available from river, lake, and so on. It could also be useful to have potable water available. So consider a simple example to illustrate how to deal with multiple water source. Limiting data for three operations are given in table 26.5. Two sources of fresh water available. Water source 1 is a concentration of 0 ppm and water source 2 with concentration of 3. So this is new. So we introduce more than fresh water. In this case, raw water available from river. So consider a simple example to illustrate how to deal with multiple water source. So two new water source, new with different concentration. The limiting composite curve for the three operation is plotted in 26.77a, this figure. A mesh against it is water supply line that is a composite of the water sources. Between 0 ppm and 21 ppm, only the WS1 can satisfy the requirement of the process. WS1 here is 0 ppm. Here, the flow rate of WS1 have been minimized to 20 ton per hour. This is dictated by the slope of the limiting composite curve between 0 ppm and 25 ppm. have here 0 to 25. So 0 to 25, we have 20 ton per hour in the water supply line. This water supply line is mixture of WS1 plus W2. The requirement of the process above 25 ppm are being satisfied by the continual use of the 20 ton per hour of the WSI and the balance by the introduction of the WS2 at 25 ppm. The amount of WS2 required can be determined by a mass balance below the page. How to calculate 9,000? 9,000 is the page. 9,000 equal to MW M water source 1 delta C water source 1 plus mass flow rate of water source 2 plus delta C. So we will have 20 times 100. When you get to mass flow rate for water source 2, which is 23.3 tons per hour. Figure 36.2070 shows the corresponding design grid for the two water sources. An additional water main is introduced into the design grid that harms the second water source. In this case, we have a full water main starting from WSI at 20 tons per hour. Next is a mixture of WSI and 93 plus 20. 93.3. 93.3 plus 20 was 150. The second waterman. Then this one is the second waterman. Okay. This is based on this operation and this table 26.5. So 40 ton per hour here. This is the final. So in this case, 20. This is in this case 20 limiting flow rate. Okay. So it's starting from 0 to 100, passing through the second waterman, which is a mixture of the two water source. So here you have 0 to 25 and 25 to 100 ppm. Oh, but the second one is from 50, but the source is from both water source until 100 ppm. So 66.7 here can be calculated, right? Okay. 5,000 divided by 75. How do you know 5,000? 5,000 is from contaminant. So contaminant here is for table 36.5. That's 5,000. 5,000 divided by 100 minus 75. So we get 66.7. About 26.7? 26.7 is based on 2,000, 0 to 100. 2,000 divided by 75. Refer to page 601. Then 13.3, the concept, we discuss the concept of changing the stream, shifting the stream from between the part 1 with part 2 to before part 1. Like this. Now, another complication that often arises is loss of water from the system. This could be, for example, the loss of water through effluent, from a housing operation, or the evaporative loss must flow from a cooling tower, neither of which become available for reuse. To illustrate how water losses can be accounted for, suppose that an operation is added to those in table 6.5 with a maximum inert concentration of 80 ppm and a flow rate of 10 ton per hour, all of which is lost. This is table 26. This is the figure 26.28, this figure shows the limiting composite curve for the three operation from table 26.5, giving a flow rate loss. Mesh again, the limiting composite curve is a water supply line that shows a change in slope. The flow rate loss occurs. The target flow rate can be determined by a mass balance below the pinch. We need to calculate the mass. So in this case, 92 ton per hour. In figure 26.28 shows the corresponding design grid for the loss. Note that no additional water main is required to account for the water loss. Loss here, yeah. How much? 10. 10 ton per hour with solution to keep it. It also be noted that the freshwater target for the three operation in table 26.5 with a single source of freshwater at 0 ppm is 90 ton per hour, which increases to 92 ton per hour with a water loss of 10 ton per hour at 80 ppm rather than 100 ton per hour. This is because water loss can be partially fed by reuse. Mhm. How it affects the water loss. So 8 ton per hour is coming from the second main. So okay, we continue. Had- So had the same loss. This is talking about water loss. Had the same loss occur with above the pinch concentration, then there would have been no increase in flow rate as a result of the fluctuation of the water loss. Finally, it should be noted that the target in figure 26.28a is based on the assumption that the loss is being fed at its maximum inlet concentration. The design procedure can be summarized in 4 steps. So set up the grid, connect operation with water main. So set up the grid is once you know the pitch, next is connect the operation with water main, correct for changes in flow rate and individual operation. So you need to calculate. Show you the graph. Remove intermediate water main and connect operation directly. Connect operation directly is something like like this. Without the intermediate water main. Without the pinch main. Okay. Table 26.6 present water use data for a simple example involving 3 operations. So 3 operations continuous starting from 6,000 to 24,000. Highest concentration is 1,000 ppm. Emitting water flow rate is 40, 20, and 80. Target the minimum water consumption for the system through maximum reuse. Design a network for the target water consumption. So figure 26.29 shows the limiting positive curve for table 26.2. Okay, so this is the composite curve. And from the composite curve, we draw the minimum water supply line. So you can determine the flow rate is 6.7. How do you know 46.7 is actually 7,000 divided by 150 at the pitch. So right now, if you want to understand why we do pitch, we do pitch because we want to know the minimum. Say the minimum energy required for the system, minimum body stress, minimum flow rate. Figure 26.3 shows the limiting capacity curve with the appropriate water supply line pinched at 150 ppm. From table 26.6, the mass load up to 100 ppm can be calculated as mass load up to pinch concentration 40, 150 plus 20, 150 minus 100. So you get 7,000 gram per. The minimum flow rate is 7,000 divided by 150. This is how you calculate it. The design to achieve the target first must identify how many regions are involved. From the limiting positive curve in 26.30, there are 2 design regions between 0 and 150 ppm, and 150 and 1000 ppm. So 2 regions below and after the pinch. Below the pinch, the first design region require 46.7 by definition. Above the pinch, the concentration change extends from 150 to 1000 ppm with the max drop of 37,000 gram per hour. So 37,000 is from the 44 divide, oh sorry, minus 7. This correspond with minimum flow rate requirement above the pitch of 43.5. So 43.5 is by dividing 37,000 divided by 1,000 minus 150. 43.52. Figure 26.31 shows the design grid for the example with the string in place. We have a 3 water main. So fresh water feed is 46.7 ton per hour and the pinch is 43.5. Infiltration is 150 ppm. The seed outlet is 1000 vm. So each stream here will have a first stream 0 to 150. Here is 100 to 800. 100 to 800 ppm here. And for operation 3, stream 3 is 700 to 1000. This is the design grid. So in case the question asks, so we need to draw it like this. No need to draw the detail. Draw this first. Figure 26.33 shows the completed network design achieving the target 46.7. So 6.7 here, you calculate it by so 2 is sorry, from 0 to 150 is 6,000. Right. 150. So 6,000. So it's 20. So the limiting water flow rate for stream 1 is this one is direct 40. Water used from the second main is 13.3 to satisfy this will become 20. And here it's 46.7. The lens out. How about this part? This part is 20. 3.5 from the first main. This one need to calculate. 150,000. Mm, 24,000. You see here, it actually reuse uh, the stream from operation to fed to the operation two. And why they reuse? Because we you cannot discharge it at 800 ppm. So at this moment they mix it with stream three, and there goes the until it reach 1,000. Note that the outlet water from operation two at 100 ppm has not been put directly into the water pump. If this had been done, this is the reason the mass balance would have been violated. Instead, further use of the water from the outlet of operation two require it to be fed to the inlet of operation three, finally discharging to the 1,000 ppm main. Figures 36.83 shows a flow sheet for the completed water network from here. Even for a small problem involving three operations, this turned out to be a solution that would be difficult to be achieved by inspection. The procedure simply allow the maximum potential for the reuse to be identified. Thereafter, the practicality must be explored and the design evolved if necessary. So the fresh water is 46.7. 40 goes to operation one from here. 13.3 goes to operation two, while 26.7 goes to everyone. And from freshwater, 6.7 plus 13.3 is 20 to operation two. So from 26.7, actually 23.5 cycle reuse for outlet from operation two and straight to operation three. This is the water network after the design. Targeting minimum wastewater treatment rate for a single contaminant. Wastewater treatment in the process industry is most often carried out in a central treatment facility. Effluent streams are collected together in a common sewer system and passed through a central treatment facility, or in some instances, given some pre-treatment and sent off to a municipal treatment facility. The problem with centralized treatment is that combining waste streams that require different treatment technologies leads to a cost of treating the combined stream that is likely to be more expensive than the individual treatment of the separate stream. What is true? If two waste streams require exactly the same treatment, then it makes sense to combine them for treatment to obtain economies of scale for the treatment. Philosophy of design is required that will allow the designer to combine effluent for treatment when it is appropriate, but also segregate them if it is appropriate. Consider now the targeting of minimum treatment flow rate for a given set of effluent streams that need to be treated to bring the concentration to below an environmental discharge limit. Figure 26.37a So this is a composite curve for waste stream. C0 to C equilibrium, CE. It shows a system with four effluent stream with different inlet concentration that need to be treated to remove mass load and bring down the concentration to an acceptable level for environmental discharge, CE. So before this, we use fresh water. This one is for wastewater. So the arrow is terbalik. This is the composite curve. F1 to obtain an overall picture rather than general than deal with four separate effluent streams. The stream can be combined together to produce a composite effluent stream. The construction is analogous to that for the limiting composite curve. The diagram is divided into concentration interval and the mass load of the stream within each concentration level combined together. Okay, this is different. The mesh load can be removed in a number of different network arrangements. The objective is designing an effluent treatment network to minimize its cost. In the first instance, this means minimizing the flow rate through the treatment process. Figure 2628 show a composite effluent curve. This is a composite effluent curve. This is the treatment line. Superimpose a treatment line representing the actual performance of the effluent treatment process. The effluent treatment process is required to remove the mass load. In order to bring down the effluent concentration to its environmental discharge limit, the steeper the treatment line, the lower will be the flow rate through the effluent treatment. The maximum slope of the treatment line in figure 26.38a is detected at the low concentration and by a minimum of the concentration. So this concentration C out minimum is based on the discharge limit. Okay. Below which the treatment cannot evaporate and the pinch point between the effluent velocity curve and the treatment line. The treatment line cannot be made any steeper than shown in figure 26.38a if the slope is increased. So if the slope is increased for the treatment line above the pitch, sorry, overlap the composite curve, then this is invisible. As it requires mass to be treated in concentration ranges. Yes, it's not invisible, so don't cannot overlap. So here is the pitch, meaning the minimum flow rate. In specifying everyone processes, two specifications are used in conceptual design. The simplest case is where the concentration at the outlet of an effluent treatment process is specified to be fixed value. So there's a two method for wastewater sorry, F1 composite curve. Either you fix the outlet value, meaning the minimum discharge limit, or removal ratio by removal ratio. So two meters. So okay. The simplest case is where the concentration at the outlet of an effluent treatment process is specified to be fixed value. Fixed value. Targeting with fixed outlet concept is illustrated in this figure. This is 21A. The effluent composite curve is first constructed. Okay, that one already. The curve line here. The order condition for the effluent treatment is specified, and the slope of the treatment line pivoted around this value until the treatment line pinches with the effluent composite curve. Pinches. See here? Until it touches the composite curve. The slope of the line will then dictate the minimum treatment flow rate. The performance of the treatment process is more likely to be specified by a removal ratio. This is what I said, removal ratio. R equal to mass of contaminant removed over mass of contaminant fed. So M mass water in representation in minus MW R C out over mass of contaminant fed. Where R is the removal ratio and the limit in and out is the net outlet flow rate, and C in is the net outlet. In many instances, the change in flow rate through the treatment process can be neglected, giving R equal to C in minus C out over C in ratio. Figure 36.9 show the construction for targeting minimum wastewater treatment flow rate when removal ratio have been specified. If the initial effluent treatment line shown dotted in figure 36.9b is considered, then there is a point of origin corresponding with this. This is a this is the second method using removal ratio. Figure 36.9b show definition for getting minimum water treatment flow rate when removal ratio has been specified. If the initial effluent treatment line shown dotted in figure 26.9b is considered, one, then there is a point of origin corresponding with a specified removal ratio. Applying the geometry of similar triangle shown in figure 39, and the engineering indicate that the ratio delta MT over MT equals the removal ratio. So in this case, the removal ratio is C in minus C out over C in equal to delta MT over MT. So what is delta MT? Delta MT is from the y-axis until the maximum C. The MT here is, so you have the initial effluent treatment line here, and this is the heat. So you get the MP plus a given removal ratio correspond with a given ratio of delta MP over MP, and therefore a fixed point of origin for the treatment line. Later we see the example. So really, in the end we get the similar remaining. If the treatment line is then pivoted around this point of origin, as shown in figure 26.39b, the ratio delta MT over MT and therefore the removal ratio are both. Finding the steepest slope where the treatment line is pinched against the opposite effluent curve correspond with the minimum treatment flow rate. This is example for fixed outlet concentration and removal ratio of 95%. The data for a wastewater treatment problem are given in table 26.8. Centralized treatment would correspond with a flow rate to be treated of 75 tons per hour. For an environmental discharge limit of 20 ppm, determine the minimum treatment flow rate. A for a process with a fixed outlet concentration of 10 ppm. B for a treatment process with a removal ratio of 95%. In figure 26.4, shows the effluent composite curve plotted for the three stream in table 26.8. So once when you get exercise test, first thing you need to do is to create the composite. The end of the effluent treatment line is fixed with a concentration of 10 ppm. And the steepest line drawn until it pinches with the effluent composite curve at 100 ppm. The removal flow rate is then given by 500. Yeah, 10 ppm. Why 10 ppm? Because the equation said so. For a person will fix on the equation of 10 ppm. From here, you get pitch at 5.4 for 5,000 per 100. So minimum flow rate is 60 ton per hour. This is the answer. How about for a fixed removal ratio with no change in flow rate? So removal ratio stated in the question is 0.95. Rearranging source in equal to 20 C out. The total mass load is given by the empty to the mass flow rate times the C in 11,400 C maximum equal to, because the delta empty is from 0 to here. Delta MC, no. Delta MC is this one with two a bit more. You get 11,400. For minimum flow rate, the treatment line will pass through the pinch point at 100 ppm. I think the mass value below the pinch point 5,400 Dividing question 26.9 question by question 26.10 give this equation. Substituting question 26.8 give a C out equal to 10 ppm. Thus C in equal to 200 ppm MW or minimum water flow rate is 60 ton per hour. By coincidence, the answer is the same in both cases, that is 10 ppm. Outlet concentration correspond with a removal ratio of um, 0.95. Yeah, that's all for targeting the water for reuse. So to recap, you have learned about how to target maximum water use for a single contaminant. This is based on limiting composite. Any question just ask. And we have a 4 step to design the water network, either for reuse or we have a new water source or to know impact of water loss. For further reading, you may check the book. This is from 593 pages up to what we learned today is until 610. Okay. So next week, we can learn about grain composition for water. What we should just show with how we do, let's see, how we do regeneration. Yeah, we learn about share with you grain composition for water next week. Also design for minimum wastewater treatment product for single units. From it, we can go to regeneration of wastewater. And the following week, we discuss about the yeah, following week we discuss about the case study. So any question you can ask or just in chat. So, for the first question, yeah, upload the video. The second question, yeah, there's no, there are software, but you can actually calculate. You have all the stream information, like what I do. It's sufficient. Yeah. But software, yes. But at the moment, our department didn't have that software. To actually find the huge one. So, thank you. You learned something. We meet again this week. Second.
Kira
On
ke
Saturday. Saturday.
Saturday. Saturday. Okay.
Oh, panas nih. Thank you.